Hello, welcome back to physics. In this lesson, we're going to continue talking about these equations of motion in one dimension with constant acceleration. Here we're going to be diving more into the meaning behind the equations. I hope that you've gotten a feel for my teaching so far in that I don't like giving equations and you just try to use them and have no idea what they're for or why they are the way that they are. It's much, much better to have an understanding of what's going on so that you're not just like just doing something for no reason. You have a real understanding of what's happening. So what we're going to do is we're going to take those three equations of motion in the last section that we kind of presented, and we showed some graphs and showed why they made sense. We didn't really derive them. You can find the derivation of those equations in your physics textbook. Ultimately, I want you to have an intuitive feel for what they mean, what they represent. So we're going to pick every term apart in those equations in this section to understand that. Then we're going to solve some problems in the next section. Let's turn to the second equation we actually produced in the last time, and that was the equation that involved velocity. V, which means the final velocity after some motion has happened, is equal to the initial velocity you start with plus the acceleration times the time. And let's just make sure we understand what this equation actually represents. So what we have here is this is the final velocity. Right? So after some time elapsed, how fast is the thing going? Obviously, it's going to depend on how fast you start going. So this is called the starting velocity. And you have to add something to that because we start off moving and then we're accelerating. So we have a term that we add to that, and that brings up the final velocity to where it is after the motion has happened. So this guy, t is obviously the elapsed time. And this a is the acceleration, which for this type of motion is a constant acceleration. A never changes in the type of motion we're considering here. So what do we have here? We have a times t. Let's look at it from a unit point of view. What are the units of acceleration? They are meters per second squared. Meters per second squared. So if we did a unit conversion type of deal where we multiplied by t is in seconds, which means we have a second up there. Notice we now have a second on the top and a second squared on the bottom. So this entire second is going to cancel with only one of the seconds down there, leaving one behind. So what you're going to have after you do this multiplication is a unit of what? Meters on top, seconds on the bottom. So what we've basically figured out is that this term ends up, when you multiply it, ends up being a velocity term, which makes sense because you're going to add it to this initial velocity to yield your final velocity. So just absolutely making sure we're all on the same page. What you start off with here is, or what you end up with is meters per second, but it has to equal meters per second on the right plus some meter per second term in this multiplication. You have to have the same units on both sides of the equal sign, and you can see that it works out because of the units. But more intuitively, what does this really mean? A times t, what does that mean? Remember from the last section, we did a quick little example. And this is why I actually did it, because I wanted it fresh in your mind. Where we started with 10 meters per second, and then we were accelerating at 3 meters per second squared. What that means is every second we increase our velocity by 3. So we started at 10, and then it went to 13, and then 16, and then 19, and so on. So it was a constant acceleration, a constant increase of velocity. So after t seconds, how much speed have you picked up? Well, you start at 10, and every single second you increase by t. So it's the same as multiplying a, the number, every time you increase by a, which is the acceleration, times the number of seconds. So like going from 10 to 13 to 16 to 19, so you can see that if you only travel for 2 seconds, then a times t would mean you pick up 6 meters per second. 2 times 3 is 6. And if you go for 3 seconds, 3 times 3 is 9, and so on. So a times t literally means I'm increasing by 3 meters per second, every second. After t seconds down the road, how much velocity have I increased? I just multiply the two. So this term literally is how much increase in velocity I have picked up over t seconds due to this acceleration. I take how much speed I've increased by, and I add it to my initial speed or velocity, and then I end up with the final number. That's what this equation means intuitively. Final velocity is equal to how fast I start at time plus whatever increase in speed I picked up over t seconds due to that acceleration. All right, very powerful stuff because, I mean, a lot of physics books don't really just tell you that. They just say, well, use the equation. And you're like, I have no idea why it's that way. All right, now this is the easiest one I think to actually understand because I can easily show you every little term. The next one I want to talk about is just as important as this one, of course. but maybe a little bit harder to pick up. So I think in order to do that, let me just see how much space I have. Yeah, I'm going to go to the other board over here. So it's the equation that involves position. So it's the final position is equal to V naught T plus 1/2 times AT squared. You're going to be using this equation throughout physics forever and ever, so kind of get used to it. Obviously, it's parabolic because we have a t squared term there. Let's quickly just talk about what the individual terms mean, and then we'll go look at units, and then we'll figure out why this does what it's supposed to do. So what we have here is this is the final position of the motion. How many meters away did the train go or something after this motion happened, right? Obviously, this is the initial velocity in meters per second. This is the time elapsed. This is the acceleration. It's a constant. This is the time elapsed. I don't need to label every little thing. The only new variable is that this is the final position in meters. How far away did I go? So the easiest way to make progress here, you know that the unit here is meters. So I'll go ahead and put that in like this. This guy, let's take a look at this term. This one's pretty easy to understand. What are the units here? V naught, the initial speed is meters per second, which is going to be something like this, meters per second. But I'm going to multiply that times time, which is also seconds. So what happens? Because of unit cancellations, the seconds cancels out with the seconds. What unit am I going to be left with? Meters, right? Meters. And notice that it all has to work out. You have to have meters on the left, and you have this term better end up being meters also. But this one, you know, you've proven to yourself also means meters. So what does this mean? Pretend you don't have any acceleration. Just cover it up. What this means is that my final position, how far away I have traveled from the starting point, is equal to how fast I'm going initially times how long I've traveled. I mean, that's just distance equals velocity times time. Basically, if you want to put it into numbers, if V naught is like 10 meters per second, how far do you go after 1 second? Well, if it's 10 meters per second, 10 times 1 is 10. I've gone 10 meters. How far away have I gone after 2 meters? Well, 10 for the first second, and then I go 10 more for the next second. 10 times 2 is 20. So I've gone 20 meters. After 3 seconds, it's 30 meters, and so on, because what you're doing is you're taking the speed, which is 10, times number of seconds. That tells you how far you've traveled. So the first term is how far I have traveled only due to my starting speed. Not because I've accelerated, not because I'm speeding up, but only because I started out at 10 meters per second or whatever it is. That's what the first term is telling you, and the units are meters because it has to be meters to match what's on this side. Now, this is the term that's actually difficult for people to figure out why it works the way it does. What we're going to do is take apart the units first to verify the units work, and then we're going to explain more about what it actually means. So let's take a look at the units here. So let's go over here and let's look at the units of this expression. The 1/2 doesn't have any units, so you don't actually write any units for the 1/2. But what is the unit of A, acceleration? Meters per second squared, right? But I'm multiplying by t squared. So you have to think for a second, but it's t squared, which means t times t. So what's the unit of time? Seconds. But it's t squared. So the unit can't be seconds because you're squaring it. It's t times t. So it's not going to be seconds up here. It's going to be seconds squared because you're taking the time. Each time variable has a unit of seconds, and you're multiplying it by itself, so that means you have to have seconds squared. So what does that mean? Seconds squared cancels with seconds squared, which means that you end up with a unit of distance, which makes total sense because the final position is going to be some distance term in meters plus some other distance term in meters. As we said all along, when you have equations, the units on the right had better match with the units on the left, otherwise it's not correct, it's not right. So you can see from a unit point of view that it all works out to meters. But why? This one's easy to understand. Velocity times time makes sense. That's how far you've gone. Why does this one give me a distance term? Well, basically the second term, whereas the first term was telling you how far you traveled only due to your initial velocity, starting speed, over that time period, this term is telling you how far I've traveled because of my acceleration. Because I start off at 10, let's just pick a number, 10 meters per second, and I'm increasing my speed the whole time. Well, obviously, I've increased beyond 10 meters per second, so however many seconds later, I'm actually going much faster. Like in the previous example on the other lesson, we started at 10 meters per second, but we ended up at the end of the motion going 25 meters per second. So clearly, the increase in speed means I'm going to be gaining ground even faster than before, and I have to somehow take that into account. So that's what the second term is. First term is how far did I go just due to my initial velocity. Second term is how far have I traveled because of my accelerated increase in velocity. So what I want to do to explain that term a little bit more is to come down. We're going to break this. This entire rest of the discussion is basically going to be talking about that just a little bit because I really want you to understand it. Basically what we have is, let's draw just a tiny little graph here. This is t seconds, and this is, let's look at the velocity, right, in meters per second. So let's say I start off this motion, just like we did in the previous problem. Let's say we start off this motion at v naught. Like in the previous problem, it was 10 meters per second. That was our initial velocity at time 0. Because it's a constant acceleration, we know as time goes on, the velocity is going to be a straight line that's going to go up. Now let's take a look how many t seconds later. Could be 4 seconds later, could be 5 seconds later. I don't know. Let's call it t seconds later. After the motion is basically done and we want to see what happens. Well, where do we end up? Well, what we figured out from before is that t seconds later, you're going to end up at some final velocity higher than your initial velocity. Of course you have to, because you've been accelerating this whole time. So we're going to say it's a final velocity of v. You can put an f, v sub I, but typically it's just called v naught, your initial velocity. Your final velocity is higher than that because you've been accelerating over t seconds. All right? So my question is, I started out pulling back from the previous example, again in the previous lesson. If we started out at like 10 meters per second, and then at the end of the motion we're going 25 meters per second, it's a nice linear increase in speed. But over that window, over that 5-second window, or whatever your motion is you're looking at, over 10 seconds or 3 seconds, or whatever your problem is, you start off with some initial speed and you end up with some final speed at the end. But during that interval, just follow me along here, even though you don't really quite understand yet exactly where I'm going. What would be your average velocity during that interval of accelerated motion? Well, if you start off here and you end up here, then you've increased your velocity, right? Obviously. How much? By? Well, subtract this minus this, we typically say that that's called delta V, right? Delta V. So in this interval here, I have gained a velocity. How much have I gained? In this interval, how much velocity have I actually gained? I have gained, in this interval, gained a velocity of, how much have I gained? We just said just a second ago, I have gained how much? A times time. Why? Because it's meters per second squared times seconds. This cancels with this, and it gives you meters per second. So how much velocity have I increased? It's whatever my acceleration is times how many seconds I am traveling. So that's how many seconds. Every second I increase by that many meters per second, because that's what acceleration is. I have gained this much velocity, but that's equal to acceleration times time. So this velocity delta here is actually equal to a times t. But then if I look at my interval here, what's the average velocity? I start out with here, I start out here, and I end up with a velocity here. Well, the average velocity, let me switch over to maybe this one. The average velocity is going to be right between those two. So the average velocity is right in the middle, like boom, right there. That's the average, right? So over this time interval window, at the beginning of the motion, I have a lower velocity than the average, and at the end of the motion, I have a higher velocity than the average. But right in the middle, I kind of hit what's the average velocity. I mean, I'm increasing the whole time, but there's an average value that would govern this motion as if I had an average velocity. What would this average velocity be? Sometimes it's lower, of course, and sometimes it's higher. But what is this average velocity? Well, it's directly between this and this. But we know that this increase in speed is this, so the halfway mark has got to be what? It's got to be 1/2 a times t. Now you can start to see where the 1/2 comes from. Okay, this is the average velocity in the interval. All right, why am I doing this? Because what's happening here is you start the clock. You start at so many meters per second, and you end up at a higher meters per second. During that accelerated motion, my speed is always increasing. But there's a representative middle point, which is the kind of the average velocity during that region. Because ultimately, I want to find out how far I travel during that region of time due to acceleration. So what I'm going to do is I'm going to find the average velocity, and I'm going to use that to find out how far I traveled. The average velocity is what? How much increase in speed I have, divide by 2, because that's the average. So this is the increase in speed. I divide by 2, that's the average. So this is the average velocity during the accelerated motion. I start here, I end here, this is the average. So then how far did I travel due to acceleration? Well, distance is equal to speed times time, always, right? So the distance traveled due to only, or I should say only, the acceleration is, that's supposed to be acceleration, sorry about that, is going to be the average velocity in that interval of motion times time. Why? Because velocity is meters per second multiplied by seconds, I get meters. Velocity times time always gives me the distance traveled. But we just said the average velocity here is 1/2 AT. That's the average velocity in that region. And so what I end up with is 1/2 A times T, that's the average velocity, times another T. That's the time. What do I get? 1/2 A times T squared. That is why this term represents how far I've traveled due to my accelerated motion. Because I start out with a velocity here. I increase all the time linearly to a final velocity here. But I can take this motion and say, what is my average velocity during this guy? Well, it's going to be the increase of my speed, which is AT, but the average was going to be half of that, but puts it here. So this is a representative middle ground because half the motion is a lower speed and half the motion is a higher speed. But if I want to find out how far I traveled, I just need to find an average. Take that average velocity times time. That's going to be how far I traveled. So average velocity times time, 1/2 AT squared. So that is why this equation is the final position is going to be how far I traveled only due to my initial speed, not increasing any speed of any kind, just my initial velocity over the time period, plus how much distance I picked up purely because I've accelerated, increasing my speed. The sum of those terms is going to give you the final position. All right? So that hopefully makes it a little clearer as to why this equation has two terms and why it's got this 1/2 AT squared, which just seems to come out of nowhere. That is the reason why. All right? Now the third equation of motion that we typically use is going to be v squared is equal to v naught squared plus 2 times a times x. So we have the initial velocity, the acceleration, and this is the distance traveled. And I don't want to derive it, I'm just going to show you the units work to make sure that you understand that. So what would be the unit over here? Meters per second squared, like this. 2 has no unit, so what you end up having over here, acceleration is, let me take out the plus. Acceleration is meters per second squared times meters now. Now that's interesting. I don't get any cancellation because I have meters on top and seconds on the bottom, but what do I get? Meters squared per second squared, which from algebra you should know is meters per second squared because I can take the square, if it's in top and bottom, I can move it out so it kind of acts on both. So notice what I have here. This is a term which is meters per second squared on the left-hand side of the equal sign. The right-hand side of the equal sign I have exactly the same unit plus another term which when you multiply it all together gives me exactly the same unit. So the units are this. So what ends up happening is if I plug all this junk in on the right and calculate something, I'm going to get v squared, the final velocity. I can just take the square root of it to kill the square term, and then I get the velocity, the final velocity. All right, again, not really deriving it. We kind of showed kind of where it comes from, but I wanted to show you that the units are consistent. So now that we've done all this talking, what I'm going to do for the most of the rest of the class is I'm going to keep these equations of motion on the board. But the equations of motion that we've talked so far, there's an important thing I want to tell you because it could cause some confusion. These equations are written assuming the motion starts at at x is equal to 0. Which most problems, honestly, are going to be like that. You're going to have a plane on a runway. It starts at the end and then accelerates. So it starts at position 0. Or you have a runner on the starting line and he starts at position 0. Or when you drop a ball later, you might say the part you drop it from is position 0 and it goes down. So you almost always have the case where you start at position 0. That's where the motion starts. But let me write the equations down, as I'm going to show you. Some books will show you a slightly different form of them. I don't want you to be confused. So x is equal to v naught t plus 1/2 a t squared. That's the position equation. The velocity equation is v naught plus a times t. And then we have another velocity equation, which can be used if we don't have time in our problem. V naught squared plus 2 times a times x. So these guys, I'm going to go ahead and just circle them, because you're going to use these pretty much all the time. But they already implicitly assume that the motion is starting at position 0. The distance I calculated is just how many meters away from 0 I end up, the ball lands or whatever. It's how many meters away from 0. Now, an alternative way that you might see these things written is the following. If motion starts at position, some location along the x-axis, x naught. In other words, if you don't start at 0, like maybe you have a runner, there's a starting line, right? But maybe he doesn't start running from there. He starts running like 2 meters from the starting line. Then his starting position would be at x is equal to 2 meters instead of at 0. Then a very, very slight change to these equations, which make them more general, is going to be this. X is equal to x naught plus v naught t plus 1/2 a times t squared. Let me get all these written down and we'll talk about them. V is equal to v naught plus a times t. V squared is equal to v naught squared plus 2a x minus x naught. So I'm going to circle these also. Now, which form of the equations you actually see in your book really is just going to depend on the book. I have lots of physics books. About half of them just give you this equation because they assume the motion starts at 0. And half of them give you this one because this one's a little bit more general if you don't start at 0. So let's take a look at what it means. The final position that your train or whatever it is lands at is going to equal to your initial position, where it starts from, plus how far it travels due to its initial speed, plus how far it travels due to its accelerated motion. All you're doing is you're taking the stuff that we have in the other equation here, and you're just adding it to wherever you start from. But if your starting position is 0, then this thing drops away, and that's why this equation is in so many physics books, because most of the time your initial position is at 0, right? That's all that is. So whatever you calculate for this, if you start 5 meters away, then you might have to add 5 to it if you start 5 meters from the origin or from the starting position. This equation doesn't change at all because there's no x in it anywhere. Final velocity is initial velocity plus a times t. This one does change slightly though. The final velocity is the initial velocity squared plus 2a, x minus x naught. This often confuses people. What is x minus x naught anyway? What it's basically saying is that if I have a graph here, right? Let's say I start, let's say this is 0, x is equal to 0, right? But let's say I don't start at 0, I start at some position x naught, and then this thing travels down the train tracks or whatever, and I stop the motion, or I stop looking at it at position x, okay? What is x minus x naught? X minus x naught is just this distance traveled delta x, the distance traveled. It's just the distance traveled. So anywhere, if you see this form of the equation, anywhere you see x minus x naught, all you need to do is think, oh, that's just the distance traveled. So if the ball went 37 meters, well, that's the distance traveled. That's x minus x naught. Now, if I started from the origin, then this is 0. So then it's just 2 times a times x, and that's why this equation is the way it is. So the bottom line is, you can use whatever equation you want to use. You're going to see me doing things a certain way, but I just want you to understand what's going on, okay? Usually I will write these equations down and just set x naught equal to 0 if I need to. But occasionally I'll get tired of doing that and I might switch back to this because most of the problems are going to assume that your motion starts at position 0. But if you have a problem where it tells you literally there are 2 horses racing horse number 1 starts 3 meters from the starting line, and horse number 2 starts from 2 meters away from the starting line. And then you analyze the motion. Then you're going to need to put the starting positions in here to keep track of it. But when you see x minus x naught, it's 2 times a times the distance traveled in the x direction. Of course, if this is 0, it's just 2 times a times x. So when you read these equations, this is implicitly telling you the distance traveled is equal to this stuff, the distance away from 0. The distance traveled is equal to this x, the distance away from 0. But if your starting point's not 0, then you might see these equations. And then the very final thing I want to tell you is that, remember a few lessons ago we talked about what we call uniform motion. Uniform motion. Uniform motion was when there's no acceleration at all, right? So remember that we had an equation for uniform motion. I don't know if you remember what it was, but think back to it and keep it in your mind right now. What are we saying? We're saying that these equations are really the real general equations of motion. Let's put a is equal to 0. If there's no acceleration at all, what's going to happen? So we go up here, let's use this version here. X is going to be x naught plus v naught t, 1/2 at squared. If the acceleration is 0, then this term just drops away. If you remember back to that lesson, uniform motion was just position is equal to the starting position plus v naught t. So this equation, if I could circle it like this is the equation of uniform motion that we said we had in the special case when the acceleration was just 0, right? So that equation of uniform motion is not a separate equation. It's not like, oh, I have to remember a uniform motion equation, and now I have to remember this equation. No, these are the real equations. It's just that when a is equal to 0, this term drops away, and this is what we call uniform motion. Same thing here. If we set a is equal to 0, all this is saying is this goes away, and it's saying that your speed is going to always equal to your initial speed, which makes sense. If there's no acceleration, then you've never sped up. It's constant uniform motion with a constant velocity. What this is saying is if a is 0, your speed at all times is equal to your initial speed, right? And then, of course, same thing here. If you set a is equal to 0, this giant term drops away for uniform motion. You'll have this squared is equal to this squared. You could take the square root of both sides, and you'll get the same thing. Velocity is going to be equal to your initial velocity for all time. So we started out by talking about uniform motion because it's simple to understand, no acceleration. It's important for you to now know, now that we're growing up a little bit, that these are the equations of motion in reality. You just put whatever acceleration you need into here to solve your problem. In fact, later on we'll be doing acceleration due to falling under gravity, and we're just going to put the value of the gravitational acceleration in there because that's going to be what we're going to be governed, or what's going to govern it. So we did a lot in this lesson. We started out by saying here is the equation of motion that deals with velocity. Final velocity is initial velocity plus how much speed I picked up due to my acceleration. It all works out from the point of view of the units. The final velocity is the final position is equal to how far I traveled due to my initial velocity plus how far I traveled due to the speeding up of the acceleration. This term is easy to visualize. This term is you have to kind of figure out that you have an initial speed and a final speed. You have an average speed. That's going to be 1/2 of a times t, 1/2 of this delta v here, which is a times t. When you take that average speed, multiply it by time to get distance, you end up with 1/2 at squared, and that's why that equation has that term in it. And then the third equation just works out unit-wise. But ultimately, what we're going to now do is we're going to turn our attention to solving problems. We're going to write down the equations of motion for every problem. We're going to look at our variables that we have been given for every problem, and then we'll formulate a strategy to solve it. Many times you'll have to use more than one equation. It only comes with practice, so let's follow along. Let's go on to the next section now and get practice with solving problems in physics with constant acceleration 1D motion.